Initially, when one opens FNIR's data in the MATLAB package Homer, one is confronted with a number of data channels. These channels differ in signal strength and noise content, and in particular, desired channels with a high signal-to-noise ratio should be isolated from the rest. For noise filtration, we initially execute a bandpass filter in the frequency domain. Through an eigendecomposition of the covariance matrix, we utilize principal component analysis to remove noisy eigenvectors corresponding to the two largest eigenvalues. Care must be taken to optimize the trade-off between noise reduction and signal retention. Next, we apply the least mean squares adaptive filter to minimize a mean squared error cost function by taking the negative of the partial derivatives in the step size with respect to entries of a coefficient vector, aka the gradient, in a transverse filter. We finally use a cross correlation to determine the lag between respiratory FNIRS noise and actual breaths. Note that the noise filtration code isn't entirely our own and was adapted from these references. Now a high SNR waveform from an FNIRS tapping protocol will be sent to the finger. It looks as follows. In an idealized system, when the time derivative of the HPO concentration is greater than 0, then brain activation is present. We iterate through the data vector and find the portions where the derivative is greater than 0, allowing us to isolate periods of activation using this code. A vector is output, illustrating the times between which the finger is tapping. This vector is fed to the Arduino integrated development environment as follows, which executes a block of code in C, triggering tapping as dictated in the MATLAB output. You can now see the FNIRS brain data activating the prosthetic. The tapping begins at approximately 7.5 seconds and stops at around 23 seconds, as expected from the displayed MATLAB output.